Hello everyone. In this video, I want to present a recreational tiling game and explore some of the mathematics related to it. The inspiration came from a hexagonal tiling that covered the floor of my first workplace. The pattern looked like this. In the diagonal rows, there are those that are completely red, and in others, the two colors alternate. In the vertical columns, every fourth tile has a different color from the base color.
This made me think there must be a simple mathematical descriptional rule that can express this type of tiling. There are two different colors of tiles, and no two blue hexagons ever touch each other. Some vertices have three red hexagons around them, while others have two red and one blue. In the end, I decided that every red tile should be adjacent to two blue ones, and every blue should be adjacent to 6 red ones. From these rules, it also followed that each red tile should be adjacent to 4 other red ones, and blue tiles cannot be next to each other. These rules can be easily summarized in a 2 times 2 matrix. Since this puzzle only existed on paper and pencil at the time, I started using letter notation along with the coloring. By modifying this matrix, different structures can be built. These are the solutions where the plane can be tiled with 2 colors. Later, I found it much more enjoyable to search for finite, connected structures than to try to achieve a complete coloring of the plane. So I began to focus on these solutions. To better understand what lies behind these structures, let's take a step back. Specifically, let's consider a single color and set the matrix value to 0. This means we place one red hexagon and no other hexagon can be placed in an adjacent position. Now, let's consider the next possibility, where the matrix value is 1. We place another tile next to the existing one. For both the original and the newly placed tiles, it holds that each has one neighboring tile of the same color. Next, let's increase the matrix value to 2. Following the analogy of the previous step, color a tile that is adjacent to both of the existing tiles. As we continue to increase the matrix value, we encounter our first significant challenge. There is no uncolored tile that is adjacent to all 3 of our colored hexagons. If we color any new tile, we must apply the same rule to it as we did to the previously colored ones. At least 24 tiles must be colored to find the smallest finite connected structure. If we increase the matrix value further, we can no longer create new finite structures. Since a hexagon can have at most 6 neighbors, if the matrix value larger than 6, we cannot meet the conditions. There are the following coloring matrix types. Coloring matrices that can create finite connected structures. Others can describe infinite structures. And coloring matrices that contain unsatisfiable conditions. Now, let's move on to 2 times 2 matrices. Each matrix essentially describes one possible permutation of relationships between the colored tiles. There are 48 2 times 2 matrices that can describe finite connected structure. Due to symmetry, it was only necessary to check the solutions of 26 matrices. These 2 matrices are 2 permutations of the same combination. The permutations of a coloring matrix can be generated by multiplying a matrix by a permutation matrix and then multiplying the transpose of the permutation matrix by this product. There are 4 such 2 times 2 coloring matrices that has only one permutation. Now we can also extend our coloring matrix types table with not connected structures. We can also distinguish some different types of finite connected structures. Another property that can be calculated from the matrix is the ratio of different colored tiles. This is simply derived from the off-diagonal values of the matrix. Using the rules laid out above, let's expand our matrix to a 3 times 3 times size. In this case, a coloring combination can have up to 6 permutations. To avoid double work, I only look for a structure corresponding to a matrix if it is impossible to generate a higher lexicographical order string from the matrix via permutation. For larger matrices, this is also advantageous because it shifts the zero values of the matrix to the right. By cutting off the last row and column disordered matrix, we are left with a smaller, still connected matrix. When deciding whether a matrix forms a finite connected structure, remember that there must be a subunit for which it is also true. Therefore, when searching for large coloring matrices, it is wise to start with smaller matrices and see how they can be extended. With this approach, I found 109 combinations of color relationships that produce finite connected solutions with 3 colors. From these 109 combinations, 580 permutations can be generated. While the ratio of color tiles is easily determined in the case of 2 times 2 matrices, in 3 times 3 matrices it is possible to create combinations where these ratios contradict each other. Let's look at an example. First, we calculate the ratios using the matrix values. Here we encounter a contradiction. How does this contradiction manifest in practice? Color a tile to green as it has the fewest neighbors. Then color its neighbors according to the matrix. Red and the blue hexagon both require red neighbor, so we can color a hexagon red. There is no green neighbor next to the newly placed hexagon, so we continue with green. Then comes a blue, followed by 2 reds. After these, the last 3 steps repeat, and every third layer doubles the number of red hexagons. But the number of available new tiles does not double every 3 years, but increases linearly. In the example shown, after the 22nd step, coloring can no longer continue due to lack of empty tiles. We can extend our table with coloring matrix types with the type of exponential coloring.
Now we are familiar with the basics. It's time to explore how many solutions in different regular tilings. So I extended my code with other regular tilings. I was particularly interested in the heptagonal tiling, because heptagons have more neighbors than hexagons, so I thought there would be more coloring matrices that could create finite connected structures. I initially believed that the 1 times 1 matrix with matrix value 3 would have an analogous solution in heptagonal tiling only with heptagonal symmetry. However, it's not the case. Upon drawing the symmetry axis, I found that they do not intersect. On any hyperbolic tiling, then only 3 1 times 1 matrices have solutions. When searching 2 times 2 solutions, we can grouping similar matrices into families. If we look at how many solvable matrices can be written per family for a given polygonal tiling, we can establish a simple empirical formula. There are 3 combinations with only 1 permutation. The formula is not valid for heptagonal tilings. There is a unique matrix that has no analogues in other tilings. Hyperbolic tilings where more than three polygons meet at a vertex. The text is even simpler since fewer matrix families need to be considered. The formula for coloring matrix combinations is as follows. For the 5 platonic solids and the 3 Euclidean tilings, such a simple formula cannot be written. All possibilities must be examined. Summarizing these values give us the following table.
Now let's look at some examples how to build these structures.
If the connection of the colors does not form a ring, we have a simple task. The construction of great circles is more complicated, but if there is a solution, it usually follows some kind of symmetry. Here is an approach to find some of them. There are also counterexamples. Pathway structures are characterized by creating a chain of ties, where every colored tie has exactly two other colored neighbors. What length of chains can be created on a given regular tiling? In the same way as in the case of searching for combinations, we have no luck with the 5 platonic solids. We have to go through all the possibilities. The characteristics of pathway structures is that the order of colored ties is repeated according to the pattern described by the matrix. Examples of the first 4 matrix sizes. But what about Euclidean and hyperbolic tilings? Let's take some examples. The shortest pathway is equal to the number of polygon faces meeting at one vertex. The second shortest pathway is obtained by running the colored ties around a polygon. Then, if we add more ties to the shape enclosed by the pathway, the length of the pathway will increase by p minus 2 times v minus 2 minus 2. If more than 3 polygons meet in one vertex, we have the option to touch the inner polygons at their edges. Each fence region will increase the pathway by v minus 2, in addition to the value we would get if the ties were in the same region. In addition, the length of our chain was also affected by the internal shape, how many vertices it contains that are not part of the chain itself. The pathway will be shorter v minus 2 times if the inner shape contains such a point. We can write the following formula. Note that if an even number of polygons meet at a vertex, it is not possible to produce an odd number of chain lengths. This is because all terms in the equation will be even. With these basics, we are now able to create a brute force algorithm that finds all the possible chain lengths. I have summarized the last non-constructible pathway lengths in the table below. Let's find the pathway where there is a repeating pattern with 4 steps on order 5 pentagonal tiling. We must check all the possible pathway lengths. The shortest pathway that can be constructed, and its length is multiple of 4, is 32 tiles long, where the pathway encloses 3 pentagons in 2 separate regions. In the next example, let's look for a structure smaller than this one. Notice that a pathway appears around the clover shape, following a red-red-blue pattern. We must check out all the possible pathway lengths with brute force algorithm for the shortest pathway length that is multiple of 3. The shortest pathway which is multiple of 3 has 12 ties. The inner shape must consist of 3 ties that touch at a vertex. We cannot build our structure from this, because one of blue ties will always have 2 empty neighbors. For the same reason, a pathway cannot be considered where the shape surrounded by the pathway contains only one internal vertex. The next option we have to try is when the inner shape consists of 6 ties and 4 vertices. This pathway can be run around so that there is only one empty tie next to each blue tie. Since all pathways with fewer ties have been excluded, this is the smallest possible structure. This pattern will be the base for some 3x3 matrices solution. Unlike planar tilings, in hyperbolic tilings the number of tiles grows exponentially layer by layer. This is also the requirement to continue coloring in exponential matrices. We must rewrite the pathway formula to recursive series. In this case there will be only one separate region. We need to rewrite that part too. In the next layer, the number of inner polygons will be increased with the previous pathway length. We also need a formula for calculate the number of inner vertices in every step. I found the following equation. We can rewrite the formula for the number of inner polygons. With these equations, we can build up recursive series for any planar or hyperbolic tiling. In the case of these tilings, the ratio of tiles in the neighboring layers approaches to a value. Now we can use these ratios in the formulas. For Euclidean tilings, Q is exactly 1 because of linear growth. For heptagonal tilings, the ratio between the layers will be the square of the golden ratio. If we observe the length of the pathways around the layers, we can see it is actually 7 times every second Fibonacci number. If we look at the conditions for continuation of exponential coloring, we can see that heptagonal tiling satisfies it.
And that's how I went from analyzing the pattern of my birthplace 4 to the ratios between layers of hyperbolic tilings. On the links below the video you can find the program that I created for visualization as well as the Excel tables. And thank you for watching.